be a better influence.
Okay. So today is mostly review, or maybe I don't know. These screens don't seem to be working. Turn them on, so I think I'm just going to turn them off. Use the blackboard instead. Does everyone have everyone get one of these sheets last time? If not, you can always get it. I still have some extras. It's on the website. You lose it. It's just a list of things. You should know. I don't claim it's exhaustive. I include arithmetic.
Is that the survey? Okay.
Yeah. So I'll just go through this and I will go through this and if there's something there's something on here you would like me to go over, I will.
Can you go over number 27?
Yes, but can we do it in reverse order?
Okay.
Oh, anything mentioned.
Okay.
There you go. You want me to think of something that it's not here, but we mentioned in class?
Actually, I want to go over the box.
That could take me a little time. Maybe we better start at the top here. So, everyone know what a function is? Know what the domain and range of a function? Inverse of a function?
What does the fourth one mean? How do you make a periodic function versus a function? I probably know what it is, but I'm trying to...
Number which?
1.4, I guess.
How can we make a periodic function inverse the function? It's in number 1, it's just the last sentence.
The last line of number
How
1.
can we make a periodic function? Oh, it's kind of, I don't know, I must have been drunk on it. How can we make a periodic, you can figure it out though. How can we make a periodic function into an inverse function? Okay, so the problem, I'm going to erase this, can I? The problem with converting a periodic function into an inverse function is the periodic function has multiple elements of its domain that go to the same place in the range. So, kind of draw a line here. We've got all these points in the range that come from the same place in the domain. I'm sorry, come from different places in the domain. So when you invert it, what happens is you have this particular value in the range now going to multiple places in the domain, and that of course would not be a function. So what you need to do is truncate that range such that you don't have that problem. So actually let me draw a good picture of a sine curve. Better picture. So, try and do this a little more carefully. And then this will come over here. So, it's kind of like the opposite of the horizontal line test. You can kind of take the vertical line test. If I have vertical lines here, right? I want each vertical line to just go through one point. So typically with the sine function, you kind of make the interval from, say, here to here.
How do you determine where that interval should be? How do you determine what interval you want?
How do you determine it? Well, if we weren't studying trigonometry and I hadn't told you what it was for the sine function, you would try and find it, the maximal interval where these horizontal lines, I mean, this is one way to think of it, these horizontal lines only hit one point. You can see, as soon as you get 2 points on either side of like a minimum, then the inverse is no longer a function. So you can, kind of look at the minimum and the maximum here as being endpoints. As I'm not going to give you some weird function, weird periodic function. Say, how do you do this, right? How do you give it an inverse? But you should know that for the sine function, I guess I kind of obscured the fact that this is now, this is the axis, this is the y-axis. You should know that the by convention we use negative pi over 2 through pi over 2. And you should, here we have negative pi over 2. Here we have pi over 2. I mean, you should understand why we're picking those points. You can say, well, why not pick from 0 to pi like we do with cosine? Well, then we have multiple points on these horizontal lines. If we invert it, that means we're going to fail the vertical line test. So that's kind of what I meant by that. It's not something you can put into like 10 words or less. Yes.
Sorry, I'm not sure what you meant by all that. So can you give us an example of a question that would come up that will touch on that piece right there? Because I didn't understand.
Which one was it?
It's the last bullet on number 1.
What we were just discussing.
Have to make. Okay.
Can you do an example?
Okay, so here would be an example where you could use your knowledge of the answer to that question. What is a reasonable domain for the inverse cosecant function? Okay. Now, you could go about it the way I just described, or you could look at this and go, that's 1 over the sine, and you say, oh, well, this has got to work with that too. A different way to answer the question, but. And for this question, this would not be the only answer. Can someone think of a? Hey, that would make it a hard question. Other than, I don't know, hard, but harder, other than negative pi over 2, pi over 2. Actually, this is not a good domain for the cosecant function. It's almost. Can anyone tell me what I need to do to that to make it a? It's kind of a notational question.
Non-inclusive?
Yeah. Why can't I?
Because the cosecant function approaches those as limits.
You know, I mean, there are all sorts of good answers. That's one. Another is that 1 over the sine at pi over 2 and negative pi over 2 is 1 over 0, which is undefined.
So you could just add 180 degrees. You could add 180 degrees to the two, well, radians in this case.
So you want to add pi to each of these?
Yeah.
That would find you another,
So that would be pi over 2 to 3 pi over 2. Let's take a look and see if that works. So pi over 2 to 3 pi over 2. And now we look, oh yeah, that works. Right? From here to here, we don't have any overlap on the y values. So when we invert it, we won't have any overlap on the x values. You guys are homing right in on the really tricky stuff here. It's fine. Okay. I hope everyone knows how to convert radians to degrees and degrees to radians. We can go over that if anyone needs to. Yes?
Well, I have a question on the different piece, if you're ready to move on.
Sure, go ahead.
What do you mean by direct angle?
Okay, if I direct an angle, if I give you a triangle, and I say, angle this, angle that, these are all just plain old, they're not directed angles, they're angles. They add up to 180 degrees. They have no direction. But if I say I have a gear, I don't want to spend a lot of time drawing a gear, and it's going this way, right? So by convention, counterclockwise is in the positive direction, and I say. I turn this gear, this doesn't sound like the question I put on an exam, but I turn the gear completely around twice. So what's the angle I've gone? 720. If I turned it the other way, negative. And of course that's really important when you're looking at the trig functions. And here we are, we start at the x-axis, and we can go in either direction. In this direction, it comes a negative angle. And unlike the angles of the triangle, which are limited, they can only go up to less than 180, these angles are unlimited. Okay? I mean, their range is negative infinity to infinity. Whereas here we have kind of these angles could be 180 to 0, except we wouldn't write it that way, right? The other way. Okay. Yes?
Yeah, if you go to a problem that incorporates numbers 9 to 10, like measures and
Sure, I can try. So my gear is going this way at 5 RPM. And this sounds a lot like something I gave you already. And its radius is 6. And it moves, we call this a rack and pinion steering, everybody? You know what rack and pinion steering is? I guess this is the rack moving, your tires are kind of go back and forth over here. And this is, I guess, the pinion. And it's turning at 5 RPM, and it's, let's say, 6 centimeters how fast is this rack moving? So that's the question, right?
So would you find the circumference of the gear?
In effect, we do, but we can start with asking the question: what is the velocity at the circumference? So before we do that, we're going to start with our 5 RPM, which is revolutions per minute. We want to convert that to radians per minute. So how do we do that? How do we convert a revolution to a radian? Yeah, so 2 pi times 5 RPM revolutions per minute equals 10 pi. I'm going to write it in. We don't usually radians per minute. Okay, so now we have radians per minute, which we often represent as omega. And then we pull off our index card or out of our brain the formula of the velocity, the circumference, I can't say it. The velocity of the circumference is equal to omega times what? R. Where R is this radius I gave you. So 10 pi radians per minute times 6 centimeters is just going to be 60 pi centimeters per minute. And that's how fast this rack is moving. I mean, we could be very, if this is like the math Olympics, right? We could have like, we have a wheel here, it's going this way, and it's, 3.5, and it's going at, let's say, 5 radians per second, and there's another bigger wheel here, and it's, 8, and then we have another wheel here, and it's only 1, and now we have another really big one here. It's going at, its radius is, 16. So which way is this going and how fast? A point on the tip of that. Now you could try and make it tricky, but that's probably not that hard a problem. Haven't you ever seen one of those, where did you see this? Exploratorium in San Francisco. They have this, this exhibit where they have kind of a motor, and it's turning a wheel, and then it's kind of a reduction gear. Like it turns a little wheel, which is attached to a big wheel. It turns a little wheel, which is attached to a big wheel. And they just have like 10 or 15 of these in a row. So at the very end, you've got motion, right? But it's like a centimeter per million years or something. So, you watch it move. Okay. That's the kind of question. I mean, the pearl of wisdom here is knowing the velocity of the circumference is v times omega r, where omega is in radians. It has to be in radians because otherwise, just multiplying radius, well, let's put this other important pearl of wisdom here. When you're talking about radian measure, the arc length is equal to what? Theta in radians times r, arc theta. That only works with radians. So if you give it something else like degrees or revolution, complete revolution, you have to convert it. Okay. I guess I don't have to say this, but assume that anytime you need to use the Pythagorean theorem, you're expected to be able to just go, oh, it's the Pythagorean theorem, of course.
What are coterminal angles again?
Just vocabulary for something I think you all know. I can come over here and clean up afterwards. So, if I have some angle here, let's call it 23 degrees. It has a kind of a starting ray and an ending ray. And you could have another angle where it has the same starting ray and the same ending ray, but it's a different angle. So those angles are coterminal. So,
Okay.
So they have the
So-
same terminating rate.
If one's 22 degrees, the other's 383 degrees. So they're
23 degrees or 23 degrees plus 180 degrees.
Wait, isn't
I'm sorry, 360 degrees.
So 380 degrees.
360 degrees.
And those are coterminal angles.
Those are coterminal angles.
You have negative coterminal angles? Like moving clockwise instead of counterclockwise?
And you could have, this angle would be, say, negative 45. And then this angle would be
I meant
negative 405. Or this angle, which is 360 minus 45, that's
350
325.
minus 45? Is it minus 45 degrees?
There we go. Coterminal angles. What else? I'll just say number 20, if I give you some function, some version of a periodic function like f of x equals, 2 cosine of beta minus, say, 20. Over 2 plus 1. You should be able to graph that. Give you some graph paper. Exchange any number here, 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 and here, and any trig function here.
This is the whole ABCD thing?
Yes. What else? I think I've been actually very, very lax about if I ask you for a specific kind of answer and you give me the other kind of answer, I haven't been haven't taken off very much. I'm not going to say if you do it the wrong way, it's all wrong, but I might rack up the tension a little. So if I say, what is the cosine of 45 degrees, and I'd like an exact answer,
Would that be radians or exact?
This is in degrees.
No, I'm saying for the exact answer you want to I'm saying in general.
The domain of the cosine could either be in degrees or radians, but its range is just a real number between what? -1 and 1. So the answer would not be radians, except in the sense that radians have no units anyway, so if you said radians, I might go, I guess so. So if you told me it's 0.70710678112, I tell you, no, it isn't. I'd be disappointed. But
What would you actually? What would you actually want?
the exact answer would be 1 over the square root of 2. And I will try and be very careful not to say, what is, right, the cosine of 45 degrees is an exact value.
In decimal form.
Well, I won't say in decimal form because you can't do it. But I might say, not using a function. Somebody got away with that. I admire that. You know, on one of the quizzes. They just said, what's the cosine of 45 degrees? Cosine of 45, they're right, but I want more from you. Okay. If you're smarter than the teacher, you get credit for it. You know, outsmart the teacher, I guess that's the best way to do it. What else?
Do we need blue books, or are you going to give us like paper like the quizzes have been? And
I don't think I'm going to give you. I think I'm going to give you tests on paper, and there'll be adequate room on it for stuff. And if you have you want to use other paper, and you want to turn it in, you put your name on it, that's fine. I'll look at it.
we'll have the entire period to be.
I think you're going to get most of it, but I don't think you're going to need all of it. I was advised by my boss to tell everyone to use the bathroom before you come, and if you need to use the bathroom in the middle of the exam, bring a note from the urologist. I'm just following directions. They tell me actually there is a bit of a problem here they have to keep on top of with honesty. Oh, I should mention this now, because it won't apply to the midterm, but it will apply to the final, that I'm required to request you come with a photo ID. Right? Really? Really? Now, you have to, if you read into that, that's, as I've asked about this is not merely paranoia on the administration's part. There have been a number of cases where
Somebody paid somebody else to take a class for them.
yes,
I've only ever actually been ID'd in a class during the final once.
I've never had. Well, they tell me I have to. So.
21.
Winter science lessons. Basically everybody said they had to get ID'd.
Okay. Let me also suggest that I think maybe everybody feels confident about this, but if I provide you with a triangle with, some letters like A, B, and C, and little a, little b, little c, that if I give you any 3 of those components, that you should be prepared to either find all the other components or tell me why you can't. And in some cases, you might actually have to provide me with 2 answers, which I think I'd be a little clear on whether I was expecting that. Under what circumstances would I expect to get more than one answer if I gave you 3 items?
Is it the SSA?
Yeah, for the SSA you might. Right, SSA, you could have 1 answer, 2 answers, or no answers.
Give us an example of that.
Sure. Angle is, I'm gonna, it won't be so obvious on the test, but the angle is 45 degrees. This is 10, and this is 1. Now you might say, well, how would I know if it's not so obvious? Right? How would you know? The calculator, does the calculator say it doesn't exist? No.
It says error.
Yeah,
Okay, well, how would you get an error? What would you type in to get an error?
well, we try and solve it.
Yeah.
Okay, well, how would you try and solve it?
But,
I'm trying to help. If you know, that's good. I'm trying to help everyone else.
yeah,
Using the law of signs.
Law of signs. Okay, so what would the law of signs say?
so you get 1/45 is equal to,
And then the sign of 45.
yeah, sine of 45, sorry.
Well, okay, that's
It could
fine.
be
Sine
sine
sine of
Can
45.
you do it both ways?
It can be sine of
They're
45.
just ratios.
Yeah, no, you can flip it over.
We should the top be sign up one?
Well, it can be sine of 45 before we can put a set or angle.
Okay, sine of 45 over 1 equals, this is, we're making believe this actually works. So 45 degrees, and that's 1. So it's this angle, right? You want to find out what that angle is. Well, let's call it x. Right?
Sine
So
of
sine of x equals over 10. Okay. Good. So now we solve for sine of x, and we get what?
10 sine 45 over 1.
And sine 45 over 1, which is, we don't have to do this exact, but it's 10 over the square root of 2. Now when we find the inverse sine of both sides,
Sine 45 should go over the square.
10 over the square root of 2, and then your calculator works.
Okay, so that's one that has 0 solutions, right?
That has no resolution.
Sure, so what about one that has more than 1?
Oh, okay.
Wait, before you move on to that,
Yeah.
so the way to essentially tell that that's not a valid triangle is because when we try and do the sine or the cosine, it just won't work.
The inverse sine or cosine. Yeah, if you're trying to find the inverse sine or the inverse cosine of something that's greater than 1 or less than -1, you can't do it. Right?
Okay,
So there's something, that's the hint that something is wrong, and it's not a triangle.
Okay.
All right, let me see if I can, all right, how about 9? So, oh, this is going to work out much better here. We're going to say 9, right?
Okay.
So 10 over 9. 10 over 9 times the square root of 2. And
Wait, how does 10 sine 45 over 9 still equal 10 over the square root of 2?
okay, so law of sines tells me sine of 45 over 9, right, the opposite side, right, has got to be equal to the sine of x over 10.
Your algebra isn't following on the next line though.
Okay. Let's multiply both sides by 10.
And 45 over 9 equals 10 over 9.
Okay. So now I want to find the inverse sine of both sides. So the sine inverse of 10 sine 45 over 9 equal to x. So what does my calculator tell me? Someone want to do it? What?
51.7. 51.78 or 52.
51.7 degrees. Okay. So, while we're on it, let's find the other angle, right? 51.7, 45. So 180 minus that is 73.7. Okay, what kind of triangle is this?
83.
Oh, 83. See, calculators are really good when you're near a blackboard. Okay, so what kind of triangle is this? We can find the other side, of course, using the law of sines again, but what kind of triangle is this? It's not isosceles. It's acute. It's acute. All the angles are less than 90. And when you see that in an SSA problem, you can kind of bet that there's going to be another triangle as a solution where it's not acute, but it's obtuse. And you can do a little geometry here to figure it out. If this is 9 and this is 9, that's an isosceles triangle. This has to be 51.7. So this angle has to be the complement of 51.7. There's 120. 128.3. Does that add up to?
22.
Oh, sorry. Okay, so this is 128.3, and then this angle is much smaller. So that's an example where you get two solutions.
So if you notice that your triangle is acute, then you could assume that there's a obtuse one of it. I'm not sure how you reach that conclusion.
If you have, you draw a picture. Picture is worth shutting up. So here's the unknown. We don't know how long this is. Here's some angle, right? So if this angle were obtuse, so this is, a long side and this is a short side, then there's no way to kind of reverse this, right? Make it work as another triangle. There's just one triangle here. But if this were, is that what I'm thinking? I'm thinking if this were 90 degrees, this is a 90-degree angle. I'm thinking,
I thought if you had a 90-degree angle SSA, you get one solution.
I don't know what I'm thinking. Well, it's a good question, right? Teacher should be responsible for explaining this clearly, shouldn't I? I think one way to think about it is in that first triangle. What did we decide the angle was? 51.
Did we use 45?
It's 51. And there was another angle, there was another solution to that inverse sine function, which gives you an obtuse angle. That's another way of thinking about it. I know that's not so clear. I mean, I guess if well, maybe it's just the length. Like if this is A and this is B, and B is greater than A, then there can only be one solution. If B is less than A, well, if B is equal to A, but we do that, B is equal to A, then these angles are the same, and there's still just one solution. If B is less than A, well, we already saw one of the possibilities down here is no solution, right? Because, B is so short it doesn't even reach. Oh, that's why I want to draw a right angle here, right? So what is a circumstance where B is less than A and is exactly one solution? It's the case where you have a right triangle, right? You have a symbol for a right triangle. Right triangle, symbol for a right triangle, right? Otherwise, there's either no solution or these are all B less than A, or there's going to be two solutions. As long as B is less than A, right, then you get kind of two solutions here. B could be like this or like this. And so this is one triangle here, and then the outer one is one triangle also. I wish there was kind of a rule of thumb where I could make that easier, but I don't think I can. I think you just have to look at the problem and figure that out. Yes?
Yeah, did you use, because I remember you used the quadratic equation to do line of triangles and that's like two possible.
There was a problem where I was trying, the question, this was on Tuesday, the question was, is there just one way to solve it? And I said, well, sometimes you could do it either way. And the second way, we ended up with a quadratic, but one of the roots of the quadratic was negative. So you eliminate that, and it was a harder way to do it. So that's, I guess that's a good question. Is there some other way to force two answers out?
Could I do the quadratic instead?
Well, let's okay. Let's look at it this way. Let's look at it this way. I'm just going to give this Z is B, so this is angle B, right? So we know that sine of B, well, this is angle A here, or this is angle A. So we know that the sine of B over B is equal to the sine of A over A. And this is what we're trying to figure out here. So we have sine of A is equal to little a over b sine of angle B. And the inverse sine A of both sides is sine inverse A over B sine of B. So in order for this to work, I need it so that, you know, you get two values out of this. One of them between 0 and 90, and another one between 90 and 180. So if this is outside of the range -1, 1, then there's no answers, right? So you can't have an inverse sine of this. Yeah, I just don't see any other way to differentiate between these two. You just have to look at it, I guess. If anybody can write that up, and you know, if they want to come in on Tuesday with a little paper explaining how to unambiguously, you know, pull that out of the equation, I will give a hefty amount of extra credit for that. Nobody's interested. Okay. Yes.
Can you read question 8 from your, this one? Question 8 from last week, that one has 2 solutions.
Okay.
And then from 3, that will really,
Okay, so I'm going to make this angle B, which is 73 degrees. Oh, by the way, if this angle here, if it's side-side angle, and this angle is obtuse, what are the possibilities? 0 or 1. I mean, just kind of visualize that. This is obtuse. You have this side, well, this might not be long enough, right? But if it is long enough, there's no other way to make a triangle out of this. Okay. Side B is 54. This is A. No, let's make this A. This is C. So A is 63. Okay, so side-side angle. Well, you can almost, you know, you can actually think about it. If this is 63 and this is 54, if you just, here, let's draw an altitude here. And now let's take side CA and reflect it, right? We know that this is valid, right? Because this is shorter than 63. So this length here has to be inside. So we already can see there are 2 solutions. And again, it's just a matter of using law of sines to figure out what this angle is, and then this angle will be its complement. That's actually some good geometry here, right? We know this angle. This is an isosceles triangle, so these angles have to be the same. And because this is a straight angle, this has to be the complement of A. So, is that enough? I mean, I could do the calculation again. But. All right, that's, you know, it's a tricky question. Okay, other things we've done. How about remember we did a bunch of problems where I gave you, running out of room, where I gave you a table and I said I wanted you to model, you to model.
You have that whole like sign function.
Yeah, well, okay, so there's an X and a Y.
This is the whole frequency and amplitude thing.
Yeah. 1, 2, 3, 4. You know, the X's are going to be at hopefully nice intervals, and then there's some values here. Recall how you would model this to a trig function?
Yeah, you start with the,
Maximum and minimum.
Okay, so you get the max, and min,
Frequency
and then the amplitude is what?
Max of whatever minus midline.
Max minus min over,
Or max, so max minus min of 2. Yeah.
And then
Okay.
max plus
and then the midline,
just the average.
so that's max plus min over 2, right? So the amplitude was like your A in that, let's say f of x. We'll make believe it's going to be a sine. E times x minus c over s e. And then the midline is what?
A T.
That's the D, okay?
E would be the period. E would be the period, so 1 over whatever.
Not the period, but B is how you find the period, okay? So you look at the data and you find the period, right?
Does it change the period then?
Sorry?
Change of period?
Change of period.
That's what
I think I heard you right, I just don't know what you're getting at. Change of
Periods 2 pi would be part of it.
Trying to figure out how B relates to the period.
Okay, so the period
Yes, right.
for a, I guess we need a little chart here. Sine, cosine, tangent. E equals 2 pi over absolute value of B, or 2 pi over absolute value of B, or just pi over absolute value of B. This is because the sine and the cosine have a period of 2 pi. The tangent's period is pi. And then you should probably also realize that the cosecant and secant, these will follow the sine and cosine. 2 pi over B, pi over B, but the cotangent, like the tangent, will just be pi over B. Because its period is also just 1 pi. Yeah, I think somewhere in there I say something like you need to know the period of these functions, you need to know where they're not defined. Where is sine and cosine not defined?
Sine is not defined in third quadrant? No, second quadrant. What do you mean? I'm sorry, I got confused myself.
Where,
No, I confused you.
sign is always defined.
Yeah, it's not undefined anywhere. It's any, the domain is any real number. Tangent is a little different, right? Where is tangent not defined?
Where cosine is 0.
Good answer. Cosine is 0. And cotangent is a little different. It's where the sine is not 0. You should be able to say, if I said cosecant of x in terms of sines and cosines, you should know that that's what?
1 over sine of x.
1 over sine of x, right? All those definitions you should know. So you can answer a question like this. Where's the cosecant not defined? Where sine of x is 0. I'm sorry. Yeah, where sine of x is 0. Yeah. Okay, back to this for a second. So now we know B. Okay? So we only have to find C. How do we find C from this data? I know it's harder. I don't have any real data to look at, but abstractly.
Looking at sine, so sine is 0 at the midline, right? And then you want to see where you should from that?
You're right. Your thinking is right, and you probably get it right. But it's D at 0, right? So sine would normally start at 0, and it would be D. So if you look at the data for where the function is D, it can either be one of two things. It can either be where the sine is going up, in which case it's at the start. This is D here now, right? Or if it's going down, well, then you have a choice. You could kind of turn the whole thing upside down, right, by putting a minus in front, right? And now this is where you're starting. So you have to do a horizontal shift to do that. I didn't explain that very well, but nobody complains. So you know what I mean. Okay, anything else come to mind? By the way, we can take a break now for a few minutes. Think of that while you're on the break. I'm going to try and get
What?
I look at my check, I look perfect. Freaking out. Hey, Fitzy.
I didn't go sit several trouble time meetings.
Dude.
In my defense, no one likes to say
It actually fits you, that's pretty cool.
I really do like how those very buttons right there.
That's pretty cool, right?
Yeah. It's like, instead of like, buttons, you know?
Yeah, we're all right.
So the thing was, there's opposite work was, so I pulled off. Yeah. Got it. What do you guys think?
Actually, no. Yeah.
That was your neighbor.
Dude, changes equals Tinder, man. Tinder.
I can't even have pretty good sleep. Yeah, it's been a while.
And I'm cold. I was gonna be cold out there.
What's your name? What's that? Rory and Beauty.
I thought you were wearing a backpack. I was like, dude, nice backpack. Trying to tip those pennies, you know? Where's my phone?
I like my home cover. It really is more about whether you can work within that environment and trust the LGT. That's what it's right?
Oh,
It's so much harder to do.
okay. Okay, I'll try that. What we were just talking about. So, this only comes up side to side. It's not a side to side angle. So side to side angle, you have one side you don't have to go. You have an angle. Now, so
No, I know.
if this side is longer, all this technically, so B is longer than A, then you can have a triangle. Where B is shorter, but also
Four is already
Yes, that's it.
Yeah, so it's like 10 more.
So that's right, okay. So if this is a right angle, that's what it's. Angle, this is an obtuse angle, then again, it's either,
Be here or at.
it's dangle there, or it's just so there's still only one triangle, or not. So those aren't really the
there's no way I'm getting
The tricky one is,
Mr. Mr.
tricky one is, now it's an acute angle.
Yeah.
And again,
Yeah.
if B is greater than A, right? If B is longer than A, then you just have one triangle. And you skip this over, it can't fit in there.
It can still be this, remember?
So,
Because, like, okay, I
and
mean, that's.
I guess this is what
We
we're
don't have to worry about test for it.
these two sides are the same somewhere.
That's not right.
So the only, again, we're narrowing it down, the only case where you might
All you do is
figure this out is where
Our
E is shorter than A.
is to E burn.
B is shorter than A, then there are three possibilities. One possibility is B is too short, and it hangs there,
And then
and that's the one where
there's
we're trying to find the
virus.
inverse
Cyrus,
sine.
what do you think about
Get it.
Cyrus?
Trying to find the
It
inverse
seems
of
like everything.
a number that's
Yeah.
greater than one.
Seems
Yes.
very fun.
I just don't know about his basic,
Other
already
possibility,
basic knowledge of.
where in this case, we just, like, one is board, here this is a right angle.
You know, like, he doesn't really have that basic.
Exactly the right length,
Honestly, it's really
comes straight down.
want to, okay.
So, having eliminated everything else, so now B is shorter than A, and you find out this angle is not a 90-degree angle.
Kind of dies.
So, here's the geometric way to look at it. Altitude here.
But,
When I take this triangle and I mirror it over here,
He's still, he's being able to.
no,
I know.
I asked him about it. but
Side B
Rich is coming up, so I'm
has
really.
to fit
And
in
then I
here.
told him to watch the.
And so this is another possible
He's
triangle.
like, I don't know how to call it.
The acute versus the two. And in that case, you can do two.
Okay.
And they're related, right? This angle here and this angle here.
It might even be lower.
So how would you, let's
And I got caught by virus, I'm just thinking, what's happening?
look at this problem here for a second.
So,
This is
I
73.
felt good about myself.
Wow.
This were longer. You don't know if 54 is long enough.
Are they just interested if you're trying to roll?
So-
Really asking about.
So we do this calculation for it here.
I don't know, we're gonna fix it. You have to be
Sine at 73 degrees.
Yeah, it's kind of hard.
4
Mine is double.
equals
Like,
sine of A.
it's what does
I mean, just felt like I felt like I offended him.
So we
Apparently when
solve for sine of A.
papers here at TBC,
You have sine of A.
he was like, hanging out.
63 was 54.
He was on the split and stuff.
Really?
So basic. Firing insurance. I don't know. Yeah, I'll keep you on there. And it's like, this is a life for me. She was like,
This turns around to
there you go. That's what we need.
That's true though. I know. Yeah.
That turns,
I mean,
That's crazy.
But I felt so bad because I was not like this child. I really wanted this position. And he's like, yeah, that was my.
But he's gonna keep up. I feel like.
No.
Yeah, see.
There was something.
it turns out to be 1.
The competitiveness.
Really competitive. Whoever is
So that tells me
just
you can't have an angle of sine where it's 1.
Yes.
So that tells me that what's happened is
Oh my goodness, what thing surprised me was that you guys have a cheaper.
54.
Yeah. It's so different, I guess. I wasn't gonna be that.
Yeah, I think that's just going through the wrong questions.
It's kind of like it was a 60. That's what it's.
I just think about, well, yesterday.
Okay, she's a little one. She was
Minus 73.
Or equals.
Well, now. Still doesn't need food.
Yeah, so it kind of changed.
All the way,
Kind of goes.
really?
I'm just saying if he doesn't, right? Or no,
Get
no.
up there, so.
And then on, Porto.
It's really tough. Okay, so that's point eight seven six five. So I find the inverse sign of that,
Oh, yeah. So she doesn't have, she have the car.
and that turns out to be 80 degrees.
Oh, yeah, so I mean, if I can't be like, oh, yeah, this is so late.
Yeah.
What do you think?
It's not that good.
One thing for sure.
I have an angle of a triangle which is.
I don't know very well.
This.
Well, looking at it, she probably worth it.
7 degrees. And now I just have to find.
And you know, it's
Also,
at least, I mean, not only, that one, but I really am not like a 3-year thing, that felt kind of but other than that, I don't know the 3-year thing, that
it's 27.
She was like,
This is something else.
and,
So we have two triangles and both.
but, yeah, but you know what, you know what's not wrong? When they I get for, I think that maybe we have like a hope for the fans, like, so, because then if they don't, then that'll go away.
They're two different triangles. No, both of these were. Both were. But now it's.
I didn't know.
I mean, we found all the angles. So now we just need to find the third side. That's good. Do you know what I'm looking for? This extra Yes, but I want something that will jump out and tell me. See, there's a possibility of no solutions.
You want to,
And there's a possibility of one solution. So under what precise circumstance? I want some top out, some calculation, and the result of the calculation is 0 to 1 or not as the value, but we look at the result, and based on the result, we can unambiguously say no solutions, black thing. Told myself how to do it, but I'm not going to tell you.
That's a good fit for me.
Other LTVs were high.
It decides for
You
30.
don't need to, right?
Goodness.
Yeah, I know,
Okay, I think we're ready. Do you have other questions, or am I going to have to generate some? Can I remind you what about 26? How to do it, yes. For number 26, I gave you a really simple example. Maybe I should make up one that's a little more complicated. not to confuse you, but just so I haven't made it so simple that leave that there. Okay, so what if I said sine of sine of 5 theta equals 0.47. Okay. So let me give you a straightforward way to go about this. First step is do the same thing to both sides, which is find the inverse sine. Sine inverse of sine of 5 theta equals sine inverse of 0.47. Okay, we're going to be real careful about this side. Let's get a number in degrees. So, do this. Okay, so we get the angle 28. I'm just going to say 28.0 degrees. And over here we just have 5 theta. But again, we want to be careful with this. I mean, right now you can see right away, just say theta divided by 5, and you get a number. And that's one of the answers. But there are other angles that the sine of is 0.47. So let's take a look at, well, I guess I have to be a little more specific here. Let's say for theta between 0 and 360 degrees. Okay? So the sine is 0.47. That's 28 degrees. The next angle that could fit this would be right, the one over here, which is the complement of 28 degrees. So that's 152 degrees. So again, 5 theta could be 152 degrees.
No, it is.
So divided by 5, that's what, about, this one's about 5.6 degrees. And 152, that's about 30.4 degrees. All right, so I'm looking for all answers between 0 and 360. So I've got my first angle, that's 5.6 degrees. My second one is 30.4. Right, here's my first angle, here's my second angle. But I kind of know that there have to be more, right? I mean, the next one to look at is what happens when we go all the way around. What angle is that? Yes, that angle is, but I want theta to be between 0 and 360. Right? Okay, so what's that angle? That's 28 degrees plus 360 is 388 degrees. So 388 degrees. 388 divided by 5 is what? 7.6. Okay, is that between 0 and 360? So that's good. The next one we want to try is this guy, 152, but again, we're going to jump all the way around. 152 plus 360, that's 512 degrees. And I'm just going to skip a step here. Divide by 5, and I get 102.4 degrees. So that's an answer. See where this is going? I just keep adding another 360 to this value and another 360 to this value. Divide by 5 and see if it's still in what I'm looking for.
So would those all be examples of reference angles?
So the reference angle for all of these angles is 28 degrees. Right? 152, its reference angle is 28 degrees. Yeah.
So for problems like this, we just go through and solve until we, for problems like this, we just go through and solve until we get a value that's.
Right. Until it's outside what you're looking for. You can kind of guess that. So what are we doing? We're adding to both of these. We're adding n times 360, right? And 152 plus n times 360. So if we do it 0, n is 0, then we get these first two, and 1, we get the next two. So then 0, we get 2 values, 1, we get 2 values, 2, we get 2 values, 3, we get 2 values. 4, we're going to get 2 values. Now, as soon as we get to 5, we're multiplying n times 360 times 5. But when we divide by 5, we're going to get a number bigger than 360. So you can already see here that there is going to be 1, 2, 3, 4, 5 times 2. We're going to be 10 solutions to this one. Now, this was a little more complicated than we've done. But you can see this kind of a general pattern here. Dividing by 5, so 5 times 2 is 10 solutions. I guess that would be the little pearl of wisdom. All right. Other questions? I'm looking for other questions. We kind of covered, in doing this, we kind of covered 19, right? How to find the values. Oh, no, I'm sorry, that's not 19. I'm thinking of something else. But you should take a look at 19. You should know exact values for anything. Sine of, n times pi over 6, or sine of n times pi over 4. If you give me an n, you should be able to figure those out exactly. And if I ask you that question, tell me what the sine of 3 pi over 4 is exactly, and you give me a calculator number, you'll probably get 1 point. If I'm feeling generous. Because that's not really what I want.
Number 20 says, be able to graph any of the functions. We mainly graph sine and cosine. Would be much of the trick of the.
I think we did homework problems.
We did all of them, but we mainly focus on the first two. Are we there's gonna be a lot of tangent graphs on there. It's like this. I mean, you only have so many hours in a day. You gotta study.
An hour and a half of writing tangent graphs. No, You need to know how to do a tangent graph. You shouldn't be concerned that I'm going to give you an exam full of tangent graphs. One of the things about drawing a tangent graph is that, I can't really, there's the A value and what the A value does to a tangent. You can't really, unless I gave you a piece of nice graph paper and wanted you to plot it, you can't really tell much from that anyway. Okay, what else? Well, let's think for a minute. If there are no other questions about this, I have a little something I want to do, which is I think will be fun, or at least for a few minutes it'll be fun. Okay, we're all ready then? We're all ready for the midterm? No. Well, you can ask questions then, or you'll have to do the preparation on your own. Okay. Yes.
Are we going to build some leaves now, or are we going?
Yes.
Yeah. Never mind.
Okay.
I think go next.
You can interrupt me while I'm going on if you have something that comes to mind. Yes.
22, you said how to model a set of data using a trace function?
Yes.
What do you mean how to model?
What I mean is something I just mentioned a few minutes ago, which is I give you a table of data,
Oh, and you read
some X's and Y's, right?
And you want to write.
And I say, I could just say, choose your own function, or why don't you model this with a sine function?
Oh, okay.
That's what that means.
For number 19, I don't know if you went over this. What does that mean?
I'm going to give it to you in the most dry possible way. Imagine you have a table, and it has all of, I'm not even going to list them all. These are in radians, right? So 0 radians, pi over 6, pi over 4, pi over 3, pi, and if you like, you can imagine this table going in the other direction, negative pi over 6. Right? And then finally it gets to 2 pi and everything repeats. Kind of repeats this way too. And now we have 6 functions here: sine, cosine, tangent, cotangent, secant, cosecant. So fill in each of these with an exact value. Now, if anyone feels like this is overwhelming, anyone feel like this is overwhelming? Okay. So, like everything else in life and math, you want to break it down. So let's just take one of them. Anyone want to pick one?
Cosecant.
Cosecant of
45.
Of pi over 4? Okay. Doesn't matter whether it's 45 degrees or pi over 4. Right. So it helps every time draw a unit circle. You don't have to. Okay. Pi over 4. This is a reference angle, right? This is in the first quadrant. And we want to find the cosecant. Is that what you wanted, the cosecant? Which is 1 over the sine is something you need to know. So now we want to find the sine of this angle. Well, it being pi over 4 or 45-degree angle, we know that it's an isosceles right triangle. And you should know, this is number 3, if the ratio of the two sides here are 1 over the square root of 2, or if you like to rationalize the denominator, square root of 2 over 2, same number. And then you can either use the idea that this is the cosine, this is the sine, or you can use opposite over adjacent, right? Opposite over adjacent is the sine. So the sine of theta is square root of 2, square root of 2 over 2, or 1 over the square root of 2. And the cosecant is the reciprocal, so the cosecant of pi over 4 is just going to be 2 over the square root of 2, or the square root of 2. And you can use that process if you know those two triangles, the 45, 45, 90 and the 30, 60, 90. If you know the ratios, you can use that process on every single one of these that isn't you know, here, 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 or here, right? And if it's on the axis like that, well, you should know sine of 0 is 0, cosine of 0 is 1. Oh, I left out something here. I left pi over 2. Sorry, there's more. Sine of pi over 2 is 1, cosine of pi over 2 is 0. You should know all those. And be aware of what happens in the different quadrants. Right, I think plus plus. What happens to the cosine in the second quadrant? Minus, plus. What about down here in the third quadrant? Minus, minus. And finally over here it's plus, minus. So you can see the cosine is always minus over here. And the sine, did I say that right, the cosine? And the sine is always minus down here. So, you know, if we ask for the sine of this value, it's going to be minus 1. Okay? Use those questions out now. Yes?
Yeah, number 4, on the revolution.
Ah,
That's just that.
I probably should have said the standard angle on a unit circle. This is very basic, but I just mean that if I give you some angle, draw a unit circle, and if I give you an angle like 10 degrees, right, you start here, and then you go 10 degrees, and that's what that's asking. That's the standard position on the unit circle. You start at the x-axis and you move your way counterclockwise if it's a positive angle, if it's a negative angle, right? Corrected angle, go the other direction. Okay. All right. Is that it? That? I have a little bit of a history lesson, which kind of ties in with what we were talking about yesterday, or Tuesday. You remember we were doing polar coordinates? Yeah. And here we have just a polar equation, r equals a plus b theta, and this is what's known as an Archimedean spiral. this will come up in a minute. But does anyone notice something predictable about an Archimedean spiral? It's something simple. It's not.
Spirals outwards.
It does spiral outwards, yes. If I were to draw a radius, though,
It goes counterclockwise.
I draw any radial line on here. You notice something about the distance between the points it intersects? All the same, yeah. That's a feature of an Archimedean spiral.
Wait, is the first one shorter though? Like the one closest to the center?
I guess so. I guess I have to repair what I said. Distance between where it intersects. If you start at the center, then no. The center has a different distance, right? It's not the center. It's where it crosses the curve. Okay. The Archimedean spiral, I assume it's attributed to Archimedes, but it's not the real popular one in math. The real popular one looks kind of like this.
The Nautilus.
Yeah, this is a Nautilus shell, but there are many other good examples. It's like a sunflower. If you look at the spirals, they're all kind of the same. And the equation for this is called a logarithmic spiral, and it has a slightly different equation. It's exponential. And I think the other day we were talking about Bernoulli. Well, it turns out Bernoulli, one of the Bernoullis, Jacob Bernoulli, or Jacobus, which is the Latin, he wanted on his grave, he wanted an exponential spiral, but he didn't get one. That's what he got. He had an Archimedean spiral.
We read Latin theory on this. What is the Latin?
I don't know. Jacobus Bernoulli, Mathematicus Incomparabilis. I think that's pretty straightforward, isn't it? I don't think I can tell you much of the rest. I guess he was an academic in Paris and Berlin. I don't know what any of it else. Okay, but anyway, just find that interesting. The other day we talked a little bit about Bernoulli, and I only knew enough to be dangerous, but so I came up with some pertinent information. So the famous Bernoulli principle comes from Daniel Bernoulli, who was, I guess he was the grandson of Nicholas Bernoulli, Nicholas I, who was the patriarch of the family. His uncle, Jacob, is the one with the spiral on his gravestone. And Jacob also had, I guess we have a little family tree here. I'll show you. Here's Jacob, and both his brother Nicholas and Johann were famous mathematicians. Daniel is the son of Johann. He's also a famous mathematician. His brother, Johann II, is also a famous mathematician. Does this like make you realize how little you and your family have done in life?
I mean, probably
I mean, you know, these guys, you know, we never see Bernoulli on an equation. Now you have to wonder which one of these Bernoullis. And Jakob II also. Yeah. And Nicholas's. And here we have the entire tree here. Hieronymus. Hieronymus is a popular name among the. All right. Well, what else? What else is there to say about this? This is of course not on any test or quiz. But the Bernoullis.
They're the ones we got.
Nothing about the Bernoullis.
Yeah, we don't know.
But there is a little bit to say. There is a little bit to say about that Archimedean, about the logarithmic spiral. Has anyone here ever heard of the golden ratio? The golden ratio. I'm going to turn this off. So the golden ratio, actually, it turns out to be 1 plus the square root of 5 over 2, which itself is not very interesting. The golden ratio is kind of like this. If you have a rectangle, and I think they use this letter for the golden ratio. If you have one side of a rectangle is I don't know what that Greek letter is. We'll just call it G for golden. And the other side is 1, so these are in the ratio of 1 to the golden ratio. And then you kind of cut off a square from that rectangle. So if you end up with a rectangle here, which is, of course, you know, the golden ratio minus 1 to 1. And it turns out that this ratio, 1 to this value, is equal to the golden ratio. And you can kind of keep doing this. You can cut off another square, and now this has the golden ratio, and so forth. Just keep cutting it down. So, you know, we could solve this here right now. We could say, let's multiply through by, I think it's a gamma. So we get gamma equals gamma squared minus gamma.
It is gamma, but gamma comes down on the left side farther.
Something like that.
That's the right side.
Oh, you mean down on that side? Oh,
Yes.
okay, thank you. I got to catch up on my Greek. So it's gamma squared minus gamma minus 1, which is, of course, a what? That's a quadratic. You can solve. So what's the solution? Well, it's negative b plus or minus the square root of b squared minus 4ac, but that's a minus, so it's plus 4 all over 2. So 1 minus that is a negative number, so we don't care about that. So that's the golden ratio. Now, I'm probably going to do this wrong, but it turns out that if you pick the right points on this, what you get, I didn't do that quite right. What you get is a exponential. You get an exponential spiral. It's these points are on that spiral. This is really cool, but it's actually not the end of the coolness here. So let's see. I guess I don't want to keep you too long. This is kind of fun, but one thing about the golden rule is I don't think anyone here has ever heard of a continued fraction. Have you? Continued fraction? So a continued fraction would be like if I said 1 plus a half plus like 1 over 3 plus 1 over 4, something like that, which could end. It could end, it could be finite, or it could go on infinitely. And it turns out that
Can you put the overhead down?
oh, sure. It turns out that if you take the golden rule and you try and write it as a, the key here is each of these numerators has to be 1, or you could write this all sorts of different ways. But if you try and write this as a continued fraction, it turns out to be 1 plus 1 over 1 plus 1 over 1 plus, this just goes on forever. Now, you might doubt me. If you want to doubt me. How do you know that? Okay. Well, let's just, without knowing what gamma is, let's just say gamma is 1 plus 1 over 1 plus 1 over. That's just some value. Actually, let's call it x. So x is 1 plus 1 over 1 plus 1 over 1 plus, going on forever, right? So let me just take a look at what's this here. This is 1 plus 1 over 1 plus 1 over, well, that's x, right? So x equals 1 plus 1 over x. And now if I multiply through by x, I get x squared equals x plus 1, or I can get x squared minus x minus 1 equals 0, and of course if I solve it, that's that equation I solved over there, and you get gamma, which is approximately 1.6 something. All right. So there's just a little more entertainment we can squeeze out of this. Okay. Has anyone heard of the Fibonacci series? Fibonacci series.
Who are you?
It's a really, I don't know if I spelled it, series. So, I'll go over here. So the way you get the Fibonacci series, the way you get the Fibonacci series is you take 1 and 1 is the starting point. And then you add the previous 2. So the third item would be 2, and the next would be 3, and the next would be 5, 8, whatever, right? 13. So it turns out if you look at this golden ratio continued fraction, you can get what we call a partial, right? So the first partial would be you just take this. So that would be 1. And then the second partial, you kind of take the next thing. That would be 2. Now the next one's a little harder here. That's, I have to take this. So what's this? This is 1 plus 1 plus 1 over 2, which is 3 over 2. I guess I'm going to write these this way, right? Now, if you take the next partial, I'm not going to figure that all out for you. I'm just going to tell you what it is. You get 5 over 3. And then, the next one you get 8 over 5. And then you get, did I say 11 here? That's terrible. 13. Nobody caught it.
You did.
13 over 8. So if you look carefully and you make believe there's like a 1 over here out, you know, in zero land, you get the Fibonacci sequence in the numerator and the Fibonacci sequence in the denominator. And each of these partials is a better and better approximation of this. Which is to say that the limit of, we'll say, Fibonacci n plus 1 over Fibonacci n, as n goes to infinity. I know some of you guys may not have seen this limit thing, but the limit is exactly, I drew it wrong there. Yeah. And I'm just going to go back to my picture here for a second. Oh, that's neat. I think it turns off. Oh. I want to show you the... Oh, I'll take the time here to warm up the cameras. So if you take a look at this... take a look at this Nautilus shell here. We just have to wait for the Nautilus shell. Warm up time. So the way this, I'm not going to be able to draw it because it's a little too small down here. The way the Nautilus shell builds its pieces is each one is effectively the next size in the Fibonacci sequence.
This is the logarithmic spiral?
And you end up with, this is kind of like in my diagram up here, you end up with a logarithmic spiral.
The same as a tree or a turtle? The same as like a tree or a turtle?
Tree? I don't think so. Rings on a tree just get bigger and bigger. There might be something like that in a tree. Turtle? I don't know. There are other animals that have constructions like this. Anyway, it's just, you know, this doesn't really, remember I was telling you that, like, we're not going to do much with polar. There's just some fun stuff with it, but this is kind of, to me, kind of the fun stuff you get with polar. Logarithmic spiral. All right, I'm not going to hold you guys anymore. Come in well rested on Tuesday. It's probably more important than staying up all night studying. I hope you won't do. Study the night.